Hi everyone, I'm going to be going over question number 24 from the Chapter 7 Bingo problems. Now this problem has to do with a block and a spring along a horizontal surface. I made a little sketch here. We've got our block, we've got a spring. The spring is compressed 0.03 meters. The spring constant is 840 newton meters, and then it also gives us the coefficient of kinetic friction, which is 0.4. And what this wants to know is if this block is released from rest, what is the speed of the block when it's moved 0.02 meters from the initial position? So it's going to be moving this way. Wants to know, after it's moved that far, what the velocity is. So to do this, we want to use our energy equation. So K1 plus U1 plus W equals K2 plus U2. So kinetic energy plus potential energy plus work done equals the final kinetic and potential energies. So from this, we can break each of these components down into their various forms. So to start out, the K1, so the initial kinetic energy, is just going to be 0 because it's from rest. So really we can just say 0 plus, and the initial potential energy is going to be, so we know we can break, I guess I'll write this down. So U1, so K1 equals 0. U1 equals 1/2 Kx1 squared. And now what we do is figure out, we plug everything in that we know. So we know that our x1 is going to be that compression, how far this block is from that equilibrium point. And so we know that it's 0.03 meters. So we get equals 1/2. We know our spring constant is 840. And that x is 0.03 squared. So when we plug all that in, we end up with 0.378 joules. So I'll erase it. We're kind of running short on room already. So, but that's how you do it. So 0.378. All right. So now we have both of our initial values. We still haven't done work yet. So let's do the work. So work, we know, is equal to negative FD. And this doesn't do much for us the way it is right now. We need to break this up even further. So we know that F equals the coefficient of kinetic friction times the normal force. So if we put this in here, we end up with negative times D. So we've broken that up a little bit more. So now we can plug stuff in. We have everything we need. So we know that the kinetic friction, so it's equals negative, kinetic friction is 0.4. The normal force is going to be, we need to break that up even more. So this actually, so we know that the normal force is equal to mg. So mg, and then that d that was on the end. So we know that the mass is 2.5 kilograms. Gravity 9.81, and then the distance, or the d, is 0.02 because that's the where we're going to end up. So now we plug that in and we end up getting, once again, I'll have to erase it to fit it all. That's how you do it. We end up that the work is negative 0.196. And that's joules. And that makes sense because, friction and everything there is going to impact that energy negatively because some of that energy is going to be lost due to friction. So it makes sense that it's negative. So that's good. Now what we need to do is figure out these values. So the final kinetic energy and the final potential energy. And so we just do the same thing. So we'll say K2 equals, so this is going to be 1/2 mv squared, and keep a 2 subscript just to make sure that it all works out. This one's 0, so we won't have a v1, but it's always good to differentiate. So now we plug in for K2. So that'll end up being 1/2 times the mass, which is 2.5 kilograms. And then we don't know this second velocity, right? That's what we're trying to figure out. So we'll leave that as v2 squared. When we multiply that, we end up getting 1.25. So once again, let me erase all this. But we know that K2 equals 1.25 v2 squared. So that's good. Now we need K1, or U12, which is our final potential energy. So we know that that is going to equal 1/2 kx2 squared. And so once again, we just plug all this in. So it's going to be 1/2 times the spring constant, which is 840, times x, which x is going to be that compression minus that. So it's going to end up being 0.01 meters. And that's the squared term. So now we just plug all that in. We end up getting the U2, so the final potential energy ends up equaling 0.042 joules. So I'll write that down. 0.042 joules. All right, so now it's kind of a lot to break it all down, but now we have these values, and so we can plug these in to this same equation. So our initial kinetic energy is just 0, so we don't worry about that. The initial potential is 0.378. And then the work is negative 0.196. And all of that equals our 1 point. I need to rewrite this where I have more room. 1 second. I have these written down on paper, so I'll just erase these. But we already worked out how to figure them out. So anyway, so once again, initial kinetic energy 0 plus 0.378 joules. I'll leave the joules off. Sometimes I get those confused for numbers. And then the work is going to be the negative 0.196. And then that equals our final kinetic, which is 1.25 V2 squared plus our final potential energy, which we found out was 0.042 joules. Well, once again, 0.042 joules. So now what we need to do is just solve for that final velocity, or V2, as I've written it here. So now it's just simple algebra. We'll move the 0.042 over, divide everything by 1.25, and then take the square root. So we end up getting 0.182. Actually, I'll kind of skip ahead. It's all just, addition, subtraction, algebra stuff. It equals 0.14 is V2 squared. And so once we square that, V2 squared equals 0.112. And then once we square that, gets rid of that, and we end up with V2 equals 0.33 meters per second. So that makes sense. I mean, it's not going very far. This distance is pretty minimal, but it ends up going 0.33 meters per second. So anyway, thanks for watching. Hope you learned something, and I'll see you in the next video. Thanks.